9.2 is the inverse of functions. And we know that to be a function, every x value has to correspond to exactly only one y value. And we can check that with the vertical line test. That's how you know if something's a function. Well, if it passes the vertical line test and a horizontal line test, that means that every x has exactly one y, and every y has exactly one corresponding x value. And if that is true, it is called 1 to 1. So if a function is 1 to 1, that means it passes both the horizontal line test and the vertical line test. So let me ask you, if I gave you function f and I said that function f is this set of points, would it be 1 to 1? Well, look at those values. And it looks like every x has a different y because no x repeats. And no y repeats either. So no y value repeats an x. So it is, in fact, a 1 to 1 function. Let's try h. Let's say that h is this function. -3, 2, 6, 3, 2, 4, and -6, 2. Now look at that one. Is that 1 to 1? Now it looks like every x is different, so no x repeats. That's good. But what do you see about this y value and this y value? So that's the same x value with the, that's the same y value with two different x values. So every y does not have one x. This y has two x's. So it is not 1 to 1. Now, if a function is 1 to 1, then it has an inverse. And you can find the inverse following these steps. And I'll write those down for you. If you want to find the inverse, what you're going to do is you are going to, first of all, switch x and y. Just trade them spots, and you'll see that in a second. And then solve for y, and you'll get a new equation. So you'll solve for y, and then lastly you want to tell them that that is the inverse. So you'll replace y with f to the -1 of x, which means that's the notation for the inverse of a function. So I'll put that up here at the top. For the inverse, it would look like that. Instead of just saying f of x, we say the inverse f of x. Okay? Okay. So, let's say that I gave you f of x is x minus 6. And I want you to find the inverse. Well, you know that f of x is the same as y. So I can replace f of x with y, and I haven't changed anything. Now I'll go to step number 1. Step number 1 says I'm going to switch x and y. So I'm going to put x here and y here, just switching them places. And then I need to solve for y. So to get y alone, I can see that I will add this 6 to both sides. So I now have x plus 6. So now I want to tell them that that's my inverse. So instead of y, I'm going to flip-flop it. I'm going to write f to the -1 of x equals, and now I'll put my x plus 6. So this is the function, and this is its inverse. And here's what's interesting about a function and its inverse. If you graph them on an xy plane, let's review our graphing. Let's graph this one first. If I want to graph that, we know that it crosses the y-axis, or its y-intercept is -6. So I'm going to go down. 1, 2, 3, 4, 5, 6. And then the slope, in front of that y is a 1, so we know that it's 1 over 1. So I'm going to go up 1, over 1. So just one of those places. And that's where I will draw that function. Now this one is x plus 6, so it crosses at 1, 2, 3, 4, 5, positive 6. And it has a slope of up 1 over 1. So it will go up 1 over 1, and I'll draw that one. Now, what's interesting about a function and its inverse is that they always reflect across the imaginary perfect diagonal. So if I were going to draw this perfect diagonal right there, we know that that's where y equals x. So in other words, I go over 1, up 1, over 2, up 2, over 3, up 3. And so y equals x. They would mirror across that line. So if I folded the graph right there, they should touch each other. They would mirror each other. That is what a function and its inverse will always do. Alright, let's try another one of those. Let's say I give you that f of x is 2x plus 3. And I want you to find the inverse and graph it. So, first of all, we know that f of x is the same as y. So not changing anything, just writing f of x as a simple y. Now we'll do step number 1. We'll switch x and y. So I just put x here and y here. Then we need to solve for y. So I'm going to subtract 3 from both sides. So I'm going to have x minus 3 over here. And over here, 3 minus 3 is gone. So it's gone. And then to get y alone, we have to divide both sides by 2. And you have to divide the whole side by 2. So here, they're gone. And so I'm flip-flopping again. I have y equals, and I have x over 2 minus 3 over 2. So we know that that is the inverse that we just found. So if I had room, I'd write one more line, and I would take that y out and put f to the negative 1 of x. So graphing those two lines, we know they should reflect across y equals x. And so I'm doing it dotted because it's just imaginary. It's not really part of the graph, but we know that they'll reflect across that. So graphing the original function first, we know that its y-intercept is 3, so I'm going to go up to 3, and the slope is up 2 over 1. So it's going to look something like that. This one we know crosses at negative 1.5. 3 halves is negative 1.5. So we're about right there. And its slope is up 1 over 2. So I'm going to go up 1, so I'm here at a half, and then over 2. So right there. And look where that one's going to draw. Ah, do you see that reflection? There's y equals x, and if I folded the graph right there, since we switched y and x, that will happen every time. They will mirror each other, reflect each other across that line. The last thing that the homework has you do is they want you to graph the inverse. And so if they gave you some graphs, for example, if they told you to graph the inverse of this, could you graph it? Because what you want to do is imagine that imaginary line right here, and so you're imagining that you're folding it, and so it's up here and coming out here. So the reflection will look like this, something like that. So if this is the f of x, this will be the inverse of f of x. So just remember to graph it. If you were to fold that diagonal line, y equals x, that's where the inverse would be. So that's 9.2. Good luck on that, you guys. Hang in there.